Ladies and gentlemen, good morning. With no exaggeration, it is an honor and privilege to welcome you here on behalf of the President of the Slovak Academy of Sciences, Martin Wenhart, to the Hall of Mirrors at the Primatial Palace for the award ceremony of the 2025 International Prize of the Slovak Academy of Sciences, which will be awarded for achievements in natural sciences. My name is Tomáš Hramatka. I represent the Academy here today, and I will do my best to guide you throughout the ceremony. They gave me all kinds of gadgets, as you might see, so if you need to ask questions and you see a blue blinking light, you know who to ask. That's why I'm here. I'm especially grateful that I can welcome our distinguished guests. Dr. Christophe Marcenat from the French Alternative Energies and Atomic Energy Commission in Grenoble, Minister of Health of the Slovak Republic, His Excellency Apostolic Nuncio, and Your Excellencies, Ambassadors of Brazil, France, Hungary, Ireland, Italy, Japan, Slovenia, Switzerland, and Ukraine, as well as the Slovak Ambassador to France. State Secretary of the Ministry of Education, Research, Development, and Youth of the Slovak Republic, distinguished representatives of Slovak universities, among them the rectors of Comenius University, Matej Bell University, and the Slovak University of Agriculture, representatives of ministries, embassies, and other state and public institutions, as well as members of the Assembly, the Scientific Council, the Presidium, and the Council of Directors of the Slovak Academy of Sciences, a former president of the Slovak Academy of Sciences, and members of the Learned Society of Slovakia, and the president of the Slovak Academy of Sciences. Ladies and gentlemen, that was a long list. Dear colleagues, friends, our ceremonies in this hall usually begin with description of significant historical events that took place here and usually involved signing of important documents. As significant as these events are, they're obviously very much unrelated to our ceremony. We are here today to add another different chapter to the book of historical significance of this very room. We are here simply to celebrate science. Science is vital for society because it provides the knowledge, technologies, questions, and solutions that we need to understand ourselves, everything that is around us, and to improve the quality of life. I mean, just look around you. Science works. We are here today to recognize exceptional scientific achievements of an outstanding scholar who will be awarded the International Prize of the Slovak Academy of Sciences. Having received the nomination from the Institute of Experimental Physics of the Slovak Academy of Sciences in Košice, the Scientific Council of the Slovak Academy of Sciences, in recognition of outstanding work related to Slovakia, awards the 2025 International Prize of the Slovak Academy of Sciences in Natural Sciences to Dr. Christophe Marcenat from the French Alternative Energies and Atomic Energy Commission in Grenoble, France. And I would now like to invite Pavol Hvizdos, our Vice President for Physical, Space, Earth, and Engineering Sciences, to deliver the laudation for Dr. Marcenat.
Good morning, ladies and gentlemen, dear friends, colleagues, guests. Christophe Marcenat is an internationally recognized physicist in the field of quantum materials. It is one of the most advanced and promising directions in the field of physics and material science. It lies at the forefront of enabling new devices and technologies for forthcoming second quantum revolution. His research focuses primarily on novel classes of superconductors. These are materials whose fundamental physical state is a macroscopic quantum coherent condensate characterized by zero electric resistance, magnetic flux expulsion, and quantization of circular currents. These unique properties make superconductors ideally suited for a wide range of revolutionary applications, from energy transmission and generation of intense magnetic fields to the development of quantum sensors capable of detecting extremely weak neural signals, superconducting electronics, and the construction of qubits for quantum computation. Dr. Christophe Marcenat has made major contributions to understanding of several types of superconductors, particularly through the development of unique microcalorimetry techniques able to probe the fundamental thermodynamic state of materials at ultra-low temperatures and under extremely high magnetic fields. Importantly, These advances were achieved almost invariably in close collaboration with the Center of Low Temperature Physics of the Institute of Experimental Physics of the Slovak Academy of Sciences in Košice, led by Professor Peter Samuely. Dr. Marsena graduated from the prestigious French École Centrale Paris, whose alumni include Gustave Eiffel, Armand Peugeot, and others. There he studied physics and material science. Following his PhD studies in Grenoble at the Centre National de Recherche Scientifique, he undertook 2 postdoctoral appointments abroad, at the Lawrence Berkeley National Laboratory in the United States and at the University of Geneva in Switzerland. There he focused on the study of heavy fermion systems. Currently, he works at the Commissariat l'Énergie Atomique, CEA, as a director of research in condensed matter physics, while also holding a position of permanent invited researcher at the Institut Néel in Grenoble, France. He is also a member of 2 internationally associated laboratories, Laboratory of Superconductivity at the Karlsruhe University of Technology and Laboratory of Quantum Materials and Circuits at the University of Sherbrooke, Quebec in Canada. He has received the 2 CA awards for outstanding research for the development of microcalorimetry in diamond and for the discovery of superconductivity in doped silicon. His collaboration with the Center of Low Temperature Physics in Košice has lasted for over 20 years now. It began with research of superconducting magnesium diboride, where a new type of superconductivity was discovered, which led to a higher superconducting critical temperature of this material. This material has since found practical applications in medical tomographs. The joint work, published in the leading physics journal Physical Review Letters in 2001, has now received over 500 citations in the Web of Science database and has earned several awards, including recognition for exceptional citation impact from Web of Science database. Another joint work with Low Temperature Center in Košice on the study of doped diamond and silicon semiconductors has yielded groundbreaking results and joint publications in leading journals such as Nature in 2006 and Physical Review Letters in 2004. Joint work by Dr. Marsena and Dr. Jozef Kaczmarczyk from Košice, including publications in Nature from year 2019 and Physical Review Letter in 2018, has provided significant insights into the nature of so-called pseudo-gaps in cuprates, as well as interplay between superconductivity and charge density waves. These results contribute to the ongoing effort to understand the mechanisms of high-temperature superconductivity, which has remained an open question for nearly 40 years since the discovery of the phenomenon. Within the framework of Slovak, French, and Japanese collaboration, the fine structure of quantum oscillation in graphite was successfully investigated, and the joint publications reporting these results appeared in Nature Communications, very prestigious journal, in 2023. Dr. Marsena collaboration with the center in Košice is a long-standing, continuing almost continuously since 2001. During this period of time, he spent more than 1 year at the Košice facilities, while our physicists spent many months concluding experiments in high magnetic field laboratories in Grenoble. As he celebrated his 65th birthday this year, Slovak Academy of Sciences decided to honor his work and collaboration with Slovak scientists and recognize his outstanding contribution to science and award him the International Prize of the Slovak Academy of Sciences in the field of natural sciences. Dear Christoph, congratulations.
We are also honored to welcome Peter Samuely, whose name you heard in the laudation just before a few minutes ago, the former Vice President for Science, Research and Innovation of the Slovak Academy of Sciences, who will now share some of his personal remarks about the award recipients. Please join me in inviting Peter Samuely to the stage.
Presidents of the Slovak Academy of Sciences, Excellencies, distinguished guests, ladies and gentlemen. Today we gather to celebrate the outstanding French scientist Christophe Marsena and to honor his invaluable achievements and remarkable collaboration with Slovakia. But regular visitors to this ceremony may notice that he is not the first French citizen to be decorated here. Indeed, Slovak-French academic connections have a long and fascinating history. Allow me to share just a few excerpts. The first known Slovak student enrolled at the Sorbonne University was Pavol de Laudatio, who studied at the Faculty of Liberal Arts in 1359. Apparently, liberalism was more popular in the dark Middle Ages than today. But also in the early 18th century, Juraj Buchholz, a paleontologist, geologist, and astronomer from Kežmarok in the High Tatras, visited Paris and established contacts with French astronomers. But exchanges went also other way around. The first head of the Department of Chemistry and Mineralogy at the Mining Academy of Banská Štiavnica, the world's first technical university, founded by the enlightened Empress Maria Theresa, was Nicolas Jacquin, a world-acclaimed scientist educated in Paris. Notably, before taking his chair, he requested a one-year delay in order to build a proper research institute and laboratory in Banská Štiavnica. Then in 1794, Antoine Fourcroy, collaborator of Antoine Lavoisier, proposed to the French Convention that the newly established École Polytechnique adopt the laboratory-based style of chemistry teaching developed in Banská Štiavnica. But there are also less fortunate stories. Maximilian Robespierre corresponded with Ignác Marničovič, professor here, urging him to organize a revolutionary movement in Habsburg monarchy. But Martinovič was soon convicted of high treason and executed in Budin, not long after Robespierre himself was guillotined in Paris. Of course, I will not attempt today to speak at length about Milan Rastislav Štefánik, astronomer at Meudon near Paris, and a French general without whom we would probably not be present in this palace at all. But France, this is not only Paris. It's also the Dauphiné, the land of future kings, with its center in Grenoble. And it was in Grenoble that the collaboration between Košice Center of Low Temperature Physics and Christophe Marcenat began more than 30 years ago. At that time, Grenoble was already acclaimed as the European capital of solid-state physics, especially thanks to the great Louis Néel, the French Nobel Prize winner and visionary, who after the Second World War built the Centre des Études Nucléaires. This is the place where Christophe is located. Also at the Institut Laue-Langevin, one of the world's leading neutron research facilities, and the Grenoble High Magnetic Field Laboratory, a joint venture between German Max Planck Institute and the French CNRS. When I arrived to Grenoble in twilight of communism in August 1989, it was a fascinating place for research. We had an access to the strongest magnetic field in the world, so whatever physical quantity controllable by magnetic field you measured, it was an unprecedented result. But I must confess, it was also my best skiing season in Grenoble. If you stayed in Grenoble for a few months, you would meet most of the world leaders and Nobel laureates in physics. For example, I still had a chance to meet 90-year-old Louis Néel when the institute was named after him. It was quite a surprise for me. I thought that such things were only possible in the Soviet Union, naming an institution after a living person, but in France as well. Soon after me, other colleagues from Košice like Pavol, Sabo, Jozef Kaczmarski, Zuzana Pribolova, and others followed, coming to Grenoble for their postdoctoral and numerous short research stays. Together we built up our own laboratory of point contact spectroscopy there and began collaborations with Christophe Marcenat, Thierry Klein, Louis Janssen, and many other Grenoblois, mostly in the field of superconductivity. The story of our common endeavor on superconductivity with Christophe successfully continues. Let me conclude my memories and souvenirs on the collaborations with a little limerick. What I'm claiming is rather clear and fair. Before we meet, dear Christophe, superconductivity was rare. Now even diamond and silicon can superconduct, and MGB2 because of two gaps. That's fact. We proved high supercurrents can bear. Vive la France, vive la Slovakia, long we are Hvizdos. Thank you.
Thank you very much for those personal remarks. And now I would like to invite the president of the Academy, Martin Wenhardt, to present the 2025 International Prize of the Slovak Academy of Sciences in Natural Sciences to Dr. Christoph Marsená. Please note that the prize itself that you can see here was designed by Marian Lašák from the Academy of Fine Arts and Design and manufactured at our own Institute of Materials and Machine Research under the supervision of our very own František Simančík. Dr. Marsená, please join us on the stage. Thank you. Thank you. We can keep the award here on the table. We will keep it. No, we can certainly. We'll keep a good eye on it. Yes. Thank you. It will wait here for you.
So, Your Excellencies, Votre Excellence, dear President, Dámy a páni, this is the point where I was supposed to give some sentence in Slovak. I have even some personal coach who taught me some sentences, but I feel a little bit stressed to really say it. So if I found a trick, I will say only two words to summarize the situation for me today. Jeden, veľký honor. Dva, ďakujem veľmi pekne. Actually, I wanted at the beginning to say that it would be, I had a difficult task to summarize in roughly half an hour more than 20 years of a scientific journey, because it was really a journey for me to work in Slovakia. But I was wrong, because almost everything has already been said by the Vice President, by Peter Samuely. So actually, the most difficult part is probably to speak after Peter Samuely, who you understood, because in the collaboration you need complementary skills, and you understood that Slovak team and Peter Samuely has the poetic side. And on the grown-up side, we have only the boring scientific part. And also, when I started to think about this presentation, which honestly I spent all my summer in my head, I wanted to start with a punchy and interesting title, and already it was quite difficult. So I stick to this title, Thermodynamics of Quantum Materials, and specifically exotic superconductors, because this is, I think, very, very the closest possible to the real work we have done in collaboration with Pozrite. So I will slowly, during my presentation, introduce and comment all these words, what does it mean exactly. So to start, I should say maybe once upon a time, because it's like a fairy tale for me. Once upon a time, in a very cold winter in Paris, in the end of the 18th century, two French physicists, Laplace and Lavoisier, designed what is called the ice calorimeter. Actually, this is just a container with three different spaces. You have an outer space which is filled by a mix of liquid water and ice. Then in the middle part, again, liquid water and ice. And in the middle, you have a small, poor little guinea pig inside. And this is called a calorimeter, and this was done to measure the heat released by the living animal inside. So it was some kind of biophysics experiments. And it's called calorimeter because this is a measure of heat. And this is exactly in a modern way, the kind of experiments I've been doing mostly, both in Grenoble and in Košice with my colleague. And actually, this is a pretty clever way to measure the heat, because the heat released by the guinea pig is just proportional to the amount of liquids that you get at the end. And the clever part, and this is a mix of liquid water and ice, and this is important in this problem. And then this is called thermodynamics nowadays. And thermodynamics, to define it, I would define this is a branch of physics that deals with heat and temperature and the relation to energy, entropy, and the physical properties of matter. After this initial experiment in the end of the 18th century, during the 19th century, there were much more improvement, more sophisticated systems, but following the same idea. And these studies actually define, I would say, the 4 important laws of thermodynamics, which are, the first one deals with equilibrium. Probably I can give you an image. If you have 2 lakes at the same altitude connected, the level of the water should be the same in every lake. Then you have actually this is 0 law. The first law is about conservation of energy. Nothing is lost, nothing is created. The second law is about entropy. So we have to define, we found that in thermodynamics we have defined a new quantity, entropy. And to give you a picture also, it means that heat spontaneously can only go from a hot part to the cold part, and never the other way around, except there is a machine in between. Also, if you want, a river can only go down. And the last law, actually, there is a minimum temperature. There's a minimum temperature, and this minimum temperature, we cannot reach it. We need an infinite number of steps to reach this temperature, meaning this is impossible. So a little bit in the same case as the speed of light. So for a massive particle, we cannot give this particle the speed of light because it will, you need an infinite amount of energy. So during the 19th century, all this law was established. And it was really important for, I said, the Industrial Revolution, the first revolution, because these revolutions were based on a machine, thermal machine, steam train, like this. And I chose this way to introduce my work, to convey probably the first important message, is the time scale of research. You see that Lavoisier and Laplace in 1783, making experiments on the guinea pig, didn't think about industrial revolution. That was just curiosity-driven experiment. And then we can say indirectly, or more or less directly, that this poor guinea pig actually induced the application of this fundamental research maybe 100 years later. And this is important to understand this time scale. I will come back to it a bit later on a more modern way, but there's always a big gap when something is done in a lab for fundamental research until you reach real daily life application in the public. So the second step maybe of my presentation is actually following these experiments also, these calorimetries, these thermodynamics. Actually, during the 19th century, there was some kind of cold race or cold war, actually, because there's a book written in it, but the English translation is not really correct compared to French. There were a cold race to reach this 0 temperature, things like this. And I put here on these slides two scales. So on the bottom one, you have the normal Celsius scale. And on top, and this is what we call the absolute scale. This is a scale for physicists. And this is the Kelvin. And because for the Celsius is completely arbitrary. We define 0, the ice melting, and 100 degrees C, the boiling temperature. But for physicists, there's no real deep meaning. The scale, the absolute scale has much more meaning. First, he introduced clearly this 0, which, by the way, is close to minus 273 degrees C, so pretty cold. And also what is really important is that temperature in this scales is directly proportional to the energy. This is, you have this formula, energy equal kBT. Meaning, for instance, temperature at 100 K is 2 times bigger than 50 K in terms of energy. And then this, as I said, in 19th century, there was this race. So these scientists started to liquefy nitrogen. Nitrogen, this is more abundant gas in this place, around 75%. So you can liquefy the nitrogen in the room, and you will get a liquid at normal pressure, which is 77 K. So you see close to minus 200 degrees C. So I still speak about these two scales, but please concentrate, because in the next slides I will use only the absolute scales. Then people liquefy oxygen, which is at slightly lower temperature, 54. Then hydrogen, and 14 K. So we are getting closer and closer to this 0. And finally, the latest element, the coldest liquid on Earth, is helium. Helium, which will liquefy, you can see on the top, at 4.2 Kelvin. This is the coldest, and this is the only element which stays liquid at T equals 0. So there was a lot of work, and I introduced these scales because all the experiments we were talking about superconductivity in Pozrite are done also at extremely low temperature, eventually extremely close to this 0. After this race, this helium liquefier, so here I just show on the right part, you have the initial liquefier of helium at Leiden University in Netherlands in 1908. And you can see the modern version in Grenoble in 2025. So it's not so different, right? So, I mean, this is amazing what people achieved more than 100 years ago. Then, of course, when you have such a new, I would say, how would call it, playground for physicists, they are really happy. You have new temperature range to go, so let's go and find some new properties of matter. What happens when the temperature goes to 0? There was strong debate among physicists at that time. So, is everything frozen? Like these cars, I don't know around which lake is it. I don't know if it's close to Košice or not, or maybe Stará Ľubovňa. And so there were a lot of debate, for instance, in metals. Because in metals, actually, the electrons are moving, they are conducting electricity. So a lot of physicists believe that when you get close to the 0 temperature, so the electrons slowly slow down, and eventually are frozen, and there is no metal at 0 temperature. And there were some other possibilities, and there was a strong debate. So in 1911, Kamerlingh-Onnes here got a Nobel Prize, actually wanted to settle this problem of at 0 temperature. So he took some mercury sample, and he made some experiments in his new liquefier that he got in Leiden, so he could reach 4.2 K. And you can see here the graph here, R versus T. R stands for the electrical resistance versus temperature. And you see that you have a finite resistance above 4.2 K, and suddenly, boom, big drop, the resistance goes to 0. And then this was an absolutely extraordinary discovery. This was the first experiment on superconductivity. But already this is pretty interesting, since, you see, to settle a really fundamental debate, he makes some experiment. And this is completely unexpected results. completely unexpected because the opposite way. We thought that electrons are frozen, and suddenly they conduct perfectly electricity. Opposite. Second point, I think, very interesting. So when you see such results, what's the first reaction of experimentalists? So say, this is completely wrong, a wire broke, there is a problem, something detached, something, there is a shortcut, something like this. So it means when we do real experiments, we are in front of unknown data, and we have plenty of such events, I would say. But how to recognize an important event from a non-important event in advance when this is the first time you see it? So many times in my career, I was looking at some data. It looks really strange. And I said, should I spend 4 or 5 years to study this, and this is just nonsense? Or maybe this is completely revolutionary. And you have no answer at that time because nobody did the experiments before you. So you are. And Cameron Holmes had the intelligence or the intuition or things to continue. And again, you see also another important point is luck, chance. Can you imagine? It shows mercury. Mercury has a TC, critical temperature, of just below, or just above, sorry, 4.2 Kelvin. Enough for the liquid nitrogen. If you have chosen some other, the experiment would be negative. So this is to emphasize this spirit of fundamental research, curiosity-driven research. And then I think there is also an extra interesting point in this incredible experiment, is that actually he continues the experiment just a few hours after, not the day after, just a few hours after, he started to pump on the helium. So when you pump on a liquid, so the temperature continues to drop. And it's noted in his book, lab book, oh, there is some strange event. The bubbles, something like this, sorry for the bubbles in the liquid of the liquid helium are disappearing. Point. And no more comment. So he took a lot of attention to this and not to this little fact of that the bubbles in liquid helium disappeared. And this bubble disappearing, this is called superfluidity. This is the equivalent for a fluid compared to superconductivity. This is for helium, becomes superfluid. This is a liquid of zero viscosity. So this is as extraordinary for a liquid. So he got a Nobel Prize for that, but he missed the other one just because he didn't notice that it was really important that the bubble were disappearing. Okay, so this was the historical part of my talk. And then, during more than 40 years, people are making many experiments on superconductors. So they found plenty of new superconductors. Most of the natural elements actually become superconductors. And there were many experiments. I will show some examples a little bit later. There were many experiments in magnetic field, superconductivity, but there were absolutely no clue, not a single idea why it was happening during 40 years. And then one of these three physicists, Cooper, had the idea that normally two electrons having the same electrical charge repel each other, but he thought that maybe in some circumstances, special circumstances, electrons could attract each other, and in this case, forming a pair. And it was actually a very important idea, because indeed, superconductivity in these metals are due that the electrons acting as a pair coherently. But it took, again, you see, 40 years to have just this idea. I wrote this mathematical formulae, which is pretty abstract. This is second quantification, just describing the operation of these pairs. But this was just to give you the message. This is really abstract. So these pairs are really complicated, and they are very fragile. So for instance, if you increase the temperature, so you break the pair. So you go back to normal metal. If you apply a too strong magnetic field, you break the pair, so critical field. You apply a too strong current, you kill these pairs. So they are in a very fragile state, and a very theoretical state, quantum state, coherent state, which are difficult to describe in the real world. I will try to show you a picture, but this is just picture. This is not really reality, unfortunately. But this is the best I think we can do. So you see first children in a schoolyard, in school. They are acting like they're playing around. So this is just to simulate the movement of random electrons in the metal. The temperature slowly goes down, go down, go down. So really it's too cold for children to play outside. So the school teacher called them, please put a ranking 2 in front of me. So the children now are in rank, and you see when they are ranking, now they can, like electrons, they can move fast in the schoolyard. It's a little bit like in this room. If we have thousands more people here and we try to move, we cannot move. And suddenly there's a nice quartet starting valse from Strauss. So the couples starts to form, we dance, and probably we can move in the room very easily because we are paired and coherently moving by the music. And this is exactly what does this pair of electrons in the superconductors. So the second probably extraordinary properties of superconductors, which are always presented, is that magnetic field cannot enter inside the superconductor. This is forbidden. So the superconductor will expel the magnetic field. And doing this, when you expel the magnetic field, you create a force, a strong force. And then you can make magnetic levitation. Magnetic levitation, and usually people you can see in Japan, they made such a levitating train, superconducting parts. And this train can go up to 600 kilometers because it is not touching the ground. There's no friction, for instance. But actually, this is more than levitation, because levitation, you can do levitation with a normal magnetic field, if you make some kind of gradient or magnetic field, but it is always unstable. This state is completely stable to superconducting hula hoops. So we'll see at the beginning. So this is a strong magnet, actually, like you put on a blackboard, and you put inside a loop like this. And then here, you put some superconductor, and you put some liquid nitrogen to making superconducting. So this is just a spacer, and you see, then after, the superconducting pellet can turn around completely freely of the things, not touching, and this is completely stable. But you can do also the opposite. You can do it outside the loop. You will see now, same procedure. So you put the things, fair, you think rotating, up, and whoa, it's not anymore superconducting, it's dropping. So you get really a completely stable state levitating. So of course, you can imagine there is some real nice application of this. So after there are, what are the applications today of these superconductors? Because the problem with these superconductors, you need a very cold temperature. So there is no real daily life application because this is too costly. This is not commercially. But in hospital, for instance, when you do, I don't say, MR image, magnetic image, you can see in CE they developed a new scanner here in Paris. So this is really recent, 2024. And you reach a magnetic field which is really high, close to 12 Tesla. And this is done by a superconductor. This ring where the body enters, this is some coil with some strong magnetic field. And this magnetic field is made with superconductors. So you need for this 182 kilometers of superconducting wires. You need a lot of liquid helium, but this is pretty, you have years of autonomy. And physicians, which are not specialists in superconductivity, can still use. And the interest, the higher the magnetic field you create, the higher sensitivity of the image. You see, for instance, you can scan really in very detail now the brain, for instance, or a body with really a high resolution. Then you have all kind of very sensitive detectors. I don't know, the Vice President mentioned it. So you can measure, for instance, here on the left, you can measure the magnetic activity of the brain. Not electrical, like usually done in hospital, but the magnetic, which is much more difficult. You have extremely very sensitive detectors in many fields, like archaeology here. But also in big science, you can create a very strong magnetic field. So probably the best example is in the Large Hadron Collider in CERN. You have a tunnel of, I don't know exactly, 30 kilometers of superconducting magnet, creating extremely strong magnetic field to focus the different beams. And this image is the construction for a fusion reactor in south of France, ITER, where we want to confine the plasma. Then you see the scale. This is the size of a man. This is the scale. And all the magnetic field will be done by superconducting materials. But again, you see that all these applications I'm showing you are really details in the hospital, in a very special international lab like CERN, where the money is not really important. It's not so big deal to cool a magnet or something, even if it costs. But in the daily life, it's difficult because, again, this high temperature breaks the pairs. The fact that superconductor could be really important is that superconductor can conduct electricity with no loss, at least in DC. And you see an example in America where they build in Long Island, I don't know how long it is, some superconducting wire cables. And in these cables, you can go through current much higher than in normal, let's say, copper cables. But just for demonstration, this is only a few kilometers or so. And the second thing is, this is an experiment in Grenoble, to store, also you can store electricity. Because in our modern life, problem with electricity, which is what is difficult, is to transport electricity, which are created in nuclear power plant or a dam, but you need to transport electricity and to store electricity. We don't know how to really store very well electricity. Batteries are not really completely efficient, and this could be a solution. So if we could find room temperature superconductivity at normal temperature, this could change really things, which would be really important. So the goal for physicists with superconductors is to increase the temperature. So also, again, the timeline of the superconductors. I said that it took 40 years to have a slightest idea why you have superconductors, pairing of electrons. And then in '86, here, poof, the temperature, big increase from 20K to 140K. So again, a factor 7. And nowadays, we are at 140K. So it's only a factor 2 compared with matter. So it's not really. And actually, recently, there are a superconductor which was discovered around 240K, but at extremely high pressure. So again, difficult to exploit in things. This was just the first part, and the second part of my talk is about what we did actually in this field in Košice with this collaboration with Grenoble. So the first really important experiment was done in 2001, actually by Peter Sabot was at that time a researcher from Košice, was a visiting professor in Grenoble, and there was some new compound which was discovered, magnesium diboride. And so the samples were prepared in Grenoble, measured by Pavol in Grenoble, sending data real-time to József Kartmáčik in Košice, analyzing data. And Peter Samuely was already writing the article because it was kind of a race. And this article got a lot of attraction because this was a real first time that were clear proof that in these superconductors you have two kinds of pairs. I put some blue arrows and red arrows, and this implies you have, normally you don't have 4 peaks in normal superconductors, but only 2 peaks. Here we observe 4 peaks because there's 2 kinds of pairs. It means that the same metal, now you have two superconductors mixed into each other. And these results were highly cited and really started strongly our collaboration because the year after, Dr. József Kartmáčik came as a postdoc in Grenoble to work with us. And just after also, Zuzana Pribuleva for a postdoc thing. And we study during these years in details these new superconductors. We call it double gap superconductivity. And then for me, started really the first time I set foot in Slovakia in November 2004. It was a train station here in Bratislava. It was very cold and rainy day, and Peter Samuely were waiting for me because we were heading to Smolenice to a SESMAG conference. And I took this picture for a cartoon. Just for me, I don't know if you realize, but I grew up in the countryside in France, in a very little village. And when I was a little boy, Slovakia was, my probably only reference was a Tintin book, a special book, where you have people in Eastern Europe speaking a strange language. And for me, it was like, again, a little bit going to the moon, and this is usually a joke I use with my colleague in Slovakia. And after this conference in Smolenice, so I went to Košice for the first time, and I received a really extremely warm welcome. And then, after that, for several years, again, I would say chance, serendipity, things. In 2004, April 1st, the Fool's Day, so announcement of superconductivity in a diamond. So superconductivity finally becomes eternal. And then there's a group in Grenoble where a lot of expecting is in growing diamond, doping diamond. For 4 years, we study diamond. And again, a new timeline, I have to go quick. But this superconductivity, again, was predicted in the 60s, again 40 years, by a theoretician, Marvin Cohen, in Berkeley, that semiconductors, in some cases, can become superconductors. And it did boron diamond. And when we were working in boron diamond with my colleague in Grenoble, and József Kartmáčik was with us, we had some discussion because silicon has absolutely the same electronic structure as diamond. So if diamond is superconducting, silicon should be. And according to the parameters, the TC should be slightly lower, but we should observe in silicon. The problem is we need to adopt a very, very high level of silicon to get something. We knew it. And I think this is the only, I think, time in my career where we predicted something, we did the work to work, we estimated the TC, we measure, it worked. This is the only time. And to summarize this, Dobra Myšlenka, and this is Etienne Bustaré. So, but the difficulty in silicon, you need an extremely sophisticated technique with laser, with melting to dope this silicon. This is this very sophisticated stuff, and we observe indeed superconductivity in silicon up, unfortunately, only 0.7 K. And now, I mean, the people are, for some time, so we were working in parallel with applied physics because silicon is so important in our daily life. This is in all the brains of a toaster, of a computer, you have silicon everywhere. So if we could make superconducting silicon, it could be a big deal. So people in applied research in CA still work to build these building blocks of superconducting electronics and things. But this is difficult to combine with. And on the applied side, they use the same laser technique to actually now integrate the transistor in the 3D, melting the surface with a laser. A further step to increase our collaboration with Sledujte was a European project, Transfer of Knowledge, which lasted three years. It was a Marie Curie action, and I was responsible for a small part of it, which was to design an AC calorimeter in Košice. And this is what we did in 3 years, actually, and this is the quantity we want to measure that was measured with a little Guinea pig at the beginning. And this is what we finally did in 3 years during this European project in Košice. We made a copy of what was done in Grenoble, ultra-sensitive calorimetry. So you have now a modern version of this ice calorimeter. This is a helium-free system. We can reach 0.3 Kelvin above the zero. So now we have the same setup in Košice, and we can really measure extremely sample, sensitive, and with very high magnetic field. And then, interestingly, for several years after, so we had more or less the same setup in Košice and Grenoble. Then it started some kind of friendly and sportly competition between us, because each time Košice had a slightly better experiment than in Grenoble. So, okay, we have to improve on our side, and we started. And we, together with this friendly and sportly competition, we increased on both sides. And now, actually, we have these setups. So on the left part, this is the equipment in Košice. In Grenoble, this is the new hybrid magnet. So we reach one of the highest fields in the world. And the 42 Tesla magnet will work in, we will make the experiment this coming December, actually. And we can make these measurements also in extreme pressure. And then the last really European project, I was involved also with Košice. This is this European microplating platform, where we, again, we work to extend this possibility of microcalorimetry at even lower temperature. And it was important to study quantum materials. And this is the final state-of-the-art setup that I will use next Monday in Košice, where we can reach temperature close to 10 milli-K, measuring extremely small crystals, eventually 10 micrograms with extreme sensitivity. And this setup is kind of unique, and this is important for them to study now some quantum aspect of some materials other than superconductivity. And I wanted to speak about a little bit second quantum revolution and things, so I'm afraid I have to skip this, and this is indeed extremely difficult. But to summarize a little bit, we are not only working on superconductors with this technique, but also on more quantum materials like quantum spin liquids, Majorana particles, and things like this. And this is one example where we see clearly quantum peaks in graphite. Okay, so now the scientific part is finished. So important things, as you said, I try to tell you a story today, some timeline, some linear line, but this is not like this in the lab. So actually there's a lot of try and errors. There's many mistakes, there's fault trails, there's dead ends, and sometimes we have chance, serendipity, things like this, but it's always curiosity driven. And sometimes it's frustrating to work in this because we don't know in which direction to go. So I have in my head a little bit a picture like this, where you have a view of a scientist walking in some quantum tunnel, and you have really strange objects. And sometimes you pick up, oh, there is nice mushrooms, or there is nice flower, oh, there is a new tree, and you want to study them. And of course, in 24 years, with the collaboration, I am in the spotlight today. like this polar bear bathing in the sun. But I didn't do this work alone. This was, of course, a collaboration. So you can see the supporting cast below the water pushing me upward today in front of you. And so I have to thank, in Grenoble, of course, my laboratory where I'm affiliated, CEA, the Néan Institute, and especially Thierry Klein, and people in the high magnetic field lab. Also, it was not only, of course, Slovak-French collaboration, because this is international. So we had also some parts from some device coming from Japan. We study quantum materials with the University of Sherbrooke. We have a very special state-of-the-art electronic made in Stockholm. So all this work also is embedded in collaborations. And then finally, the Slovak team in Košice. I'm really, because the best, I say honestly, the best part of the prize today for me is that my collaborators in Košice thought that I deserved this prize, and they submitted my nomination. So this is, for me, what I'm most proud of. Thank you, Košice. I will come back. Okay, this was just a final joke that we made also sometimes some crazy experiments, like the little guinea pig at the beginning. So we went with Josef Karmačík in one of the highest peaks in Slovakia, officially to test room temperature superconductivity, but don't ask too many questions, please. And finally, most important, it was a lot of fun during these 24 years for this collaboration. Thank you for your attention. Sorry I was so long. And yes, I don't know what to say more. Thank you.